on this computer. Nope, I'm having a little issue over here on the sound side myself, but we'll see. All right, so maybe not, we'll see. Okay, so this week, it's the 8th week of class. We only have 7 more weeks to go, including finals. So we're at the halfway point. So, you know, don't be scared. We have a lot to do. We only have a total of 11 modules. We're on module 6, so we're looking pretty good there. One of those modules is kind of small too. Radicals only takes a day. So, but other than that, things for this week, we have modules 1 and 2 homework due by Friday, if we get through everything, which we should. And then we will probably have our module 7 start the next day after that. Okay, on our schedule here, the whole week of October 12th through 16th is supposed to be on module 6. And so that's great. That's exactly where we are, and that's what we're going to do. Next week, we're going to have module 7, but we're also going to have a group activity on SN1, SN2, E1, E2. So what we'll be able to do is kind of differentiate between those two, look at solvents and steric effects, and try to figure out what's the most likely mechanism, and then what the products might be for the 2 or 3 possible mechanisms available to us. And so that's a group activity we'll have next week. But for this week, let's focus on getting our reading done for chapter 6, both sections 1 and 2, and getting those assignments in. Again, if we don't come completely through it this week, I will push that to Monday, but I'm hoping we get through it this week. So that gives us, the only things due this week are coming to class and getting that homework done. I'm setting up a set of additional questions that, if, especially for this chapter here, that might be better to do you know, as extra practice, but I'm going to set them up after you turned your homework in so you can use them as a review for our next test. By the way, our next test is October 30th. So you'll be able to, you know, have your test on Friday and then get all sugared up. 2 things I want to mention is early voting starts tomorrow. And there is an early voting site here on campus. Go ahead and go to the Hays County voter website. It's actually on CML and it's at the PAC. It starts as early as 7 a.m. some days through the next 2 weeks. So go ahead and get your early voting in. That'll help you not having long lines. Hopefully you've already registered to vote. The deadline for that passed last week. So also for those of you who know what today is, happy Indigenous Peoples Day. So, all right, any questions about that before we begin? All right, I don't see anybody unmuting and nobody in the chat. So we're gonna go ahead and share my screen and continue on with module 6.1. Okay, so I'm gonna share my screen and move my gallery view up over here. Okay, and don't forget to go to your SI sessions this week. It's going to be a lot of the review of stuff we've done this past week and get a nice grounding in these basic ideas here. So don't forget to go to your SI sessions. Okay, so we started on this chapter here before, but we actually got all the way down to the point where we were talking about different mechanisms and how we use these arrows to push things around so you know which electrons are being used to make which bonds, okay? And we also know which bonds will break to make which charges or electrons. And so you can do this with charge or without charge, but the idea is you typically have a lone pair or a negative charge are the electrons that reach out and form the new sigma bond. So that is a very important way. And we're going to use this again and again, especially in chapters 6.2. So don't forget this. This is important. But the next most important thing I want to talk to you about is what we call carbocations, okay? And the thing about carbocations is just like when we were looking at different possible things of reactions that can happen. One thing can happen, we can break a bond and form 2 ions. And in this case here, we broke a bond and formed a positive charge on carbon, or a carbocation. So those are the things we're going to talk about today. Excuse me. Sorry, the mold must be up. All right, so that being said, let's go ahead and talk a little bit more about carbocations. Okay, before we can talk too much more about what they do and how they change, let's talk about the classifications of them. We have three different classifications of carbocations. We call them primary, secondary, and tertiary. Okay, so typically we use the number 1 with a dot for primary, a number 2 with a degree sign, and a number 3 with a degree sign for primary, secondary, and tertiary. Okay, so they have different stability, so knowing which kind they are is very important, being able to identify them immediately just by looking at them. So the key here is that a primary carbocation is one with only one substituent. Okay, so that means if we had a CH3 and a carbon, and let's put 2 hydrogens on it, such that it has almost, and it has a cation on it, that is a primary carbocation. It has 1 carbon attached to it. Now we also have what we call a methyl cation, which we never form. It's very hard to do. You can only form at high temperature and gas phase, where you have your, let's change color here to blue, where you actually have 3 hydrogens on here and a positive charge. And we call that a methyl cation, okay? But we hardly ever see it, so we just want to differentiate that it's not a primary because this one has 1 other carbon attached, okay? So in the case of a secondary carbocation, I'm gonna go to stick figure drawing now. That's where we have 2 other carbons attached to the carbon with a positive charge. And then of course, we have our last one, which is 3 other carbons attached. So if you can imagine, this is 3 different methyl groups here. Okay. So they each have a structural difference. And so when you have 2 hydrogens on your carbocation, it's a primary carbocation. When you only have 1 hydrogen on that primary, on that carbocation, it's a secondary. And when you have no hydrogens on that carbocation, we call that a tertiary. So, but most commonly use the number of carbons that you see attached to that carbocation carbon. Okay, so now that we can recognize them, we have to understand that they have different stabilities, okay? So tertiary carbocations are more stable than secondary carbocations, which are much more stable than primary carbocations. So let me draw that out for you right here. We're gonna say that tertiaries are the most stable. Secondaries are more stable than primaries, but primaries are much, much less stable than secondaries. So tertiary is the most stable. Secondaries form, but it's not as common, and primaries hardly ever form. Okay, so the whole reason behind this is 2 things. We have what we call the hyperconjugation effect, which is a through space sharing of electrons, and an inductive effect, and that's through the sigma bond sharing of electrons. Okay, and so let's talk about both of those different effects right now. Okay, so in the case of this, I'm going to use this drawing right here and show you that in the case of the inductive effect right here, when we have a carbocation here, we have carbons that have all the same electronegativity, right? But now that you have a positive charge on that carbon, it can actually donate a little bit of its electron density toward that carbocation, and each of those carbons can do that, right? Okay, so we have 3 sigma bonds that can donate electron density to stabilize that charge. Okay, if we only have 2, we only have 2 sigma bonds that we can have carbons donate here. So that's 2 sigma bonds. And the hydrogen is actually more electronegative. So it cannot donate electrons to the system, okay? So there is no inductive effect from a hydrogen, therefore only the carbons give a role in that inductive stability. Now, if we go down to the primary, we only have 1 carbon, so only 1 sigma bond can help stabilize that charge, okay? So do we see why the tertiary carbocation is more stable just from an inductive effect? You can spread that positive charge out a little bit by having, it's less of a positive charge because you have a little bit being donated from 3 carbons. You have a little bit more of a positive charge because it only have 2 carbons donating, you have a little bit more positive charge. And then when we get to our methyl here, that's the least stable of all. And again, we hardly ever see that happen in our reactions. So in addition to that, we also have the idea that with a carbon here, you have a hydrogen here, and this does have an electron cloud on it and can donate a little bit of electron density through space, not through the bond, but through space. That's what we call hyperconjugation. So those hydrogens, and imagine you have 9 little hydrogens here, and they're each donating maybe 1/100th of 1%, but that's still enough to give it that through space interaction, or the hyperconjugation reaction. And notice you have more hydrogens here than here than here that have that through space interaction. So again, it leads to the greater stability of the carbocation. So the tertiary is always the most stable and actually forms fairly easily. And we can change things to make a good leaving group or a better solvent to make it even happen faster. Our secondaries are next most common, and it very dependent upon the leaving group and the solvent. Sometimes it won't form the carbocation. Sometimes it will form the carbocation, but we have to look for solvent and leaving group to do so. These rarely happen in any of the systems we use, but we need to know that they are there and are possible in some rare cases. Okay, that being said, so we want to think that if tertiary carbocations are the most important, or I'm sorry, the most stable one, those are the ones we're going to use the most in our chemistry. Okay, so this is kind of a visualization of the hyperconjugation available to us from those carbocations. Okay, so one of the things we can think of is that these hydrogen clouds on the outside, well, they are not going to inductively give that charged species. It actually has a through space interaction that allows you to do it. And that's that hyperconjugation effect. The other thing we need to know about carbocations is that the carbon in the middle has only 3 carbons bonded to it, right? So it has changed hybridization. The carbon in the middle of here is an sp2 carbon that is bonded by sigma to 3 other carbons here. So where's that other p? Okay, we only use 2 of the 3, so where is it? Well, it turns out that p orbital is above and below that plane made by the sp3. Remember, the sp3, sp2 is 120 degrees apart, and it's trigonal planar, so it's flat, right? So where's the p? The p is above and below that plane. And so this p orbital is empty and therefore has a positive charge on it. Okay, so this structure is very important because if you had to change hybridization from sp3, which is tetrahedral, to sp2, which is trigonal planar, and now we have a free orbital that's empty with no electrons above and below the plane, that's going to control where our reaction happens, right? Being that when our electrons come in and make our new bond, it has to come above or below this plane. And that's going to play a role in our products. Okay, so now that we know that our sp2 hybridized carbon here is a nice trigonal planar carbon, and we have that empty orbital above and below the plane, we can also see that the hydrogens that are sticking up over here can donate slightly to that empty p orbital, okay? Remember, that inductive effect is directly through the sigma bond. Hyperconjugation is from those hydrogens that can help stabilize that empty p orbital. Okay. All right. So tertiaries are more stable than secondaries, and secondaries are more stable than primaries, right? So one of the reasons we know this is because if it's given the opportunity, i.e. has a good solvent that it likes to do this in, it will rearrange. remember, one of those types of reactions we had besides breaking a bond to form the carbocation, we also had a rearrangement, okay? So in this case, carbocations like to rearrange to get to the more stable carbocation if at all possible, okay? So if you have a secondary, it'll transition to a tertiary. If you have a secondary, but you can't turn it into a tertiary, it does not rearrange. If you already have a tertiary, it will not rearrange. It only occurs when you can form a more stable carbocation. So the most commons are from primary to secondary or from secondary to tertiary. It's never just going to the same one. Okay, so how do we do this? Okay, we have two options available to us to go from a secondary carbocation to a tertiary carbocation. And one is called a hydride shift and one is called a methyl shift. So as the name suggests, we're moving a hydrogen from a carbon that is 1 over from our carbocation. We're going to shift that hydrogen and its electrons over to that carbon that is less stable carbocation to form a more stable carbocation. Okay, so that's what we call a 1-2 hydride shift. We're shifting from one carbon over to the second carbon and giving it to a more stable tertiary carbocation. Okay, but we don't only do it with a hydrogen, okay? Notice I said hydride shift, okay? It's not a proton shift. Proton is where it leaves without its electrons. Hydride is where it leaves with its electrons because a hydride is actually a hydrogen with a negative charge. So we're actually moving the hydrogen and both of its electrons over one carbon. Okay, the next thing we can do is we can actually do a methyl shift. It won't work with larger things, it only works with methyls. We can actually move a CH3 one carbon over. We call that a 1-2 methyl shift. And again, it takes its electrons and puts it over here. And the carbon where the methyl was now has that empty p orbital. Okay, so what does this look like? Okay, so what this looks like is we have our 1 carbon, which is the 1 carbon, and we have our 2 carbon here, okay? So in this first case right here, we have a secondary carbocation, okay? We have an opportunity that if we move this hydrogen right here over to this position here, notice this is our secondary carbocation, and this is not a carbocation at all, okay? So if we move that hydrogen over, we'll have 1, 2, 3 carbons attached to this carbon. That would turn that carbon into a tertiary carbocation. So the idea is we take both electrons, move it over to this positive charge, creating our new sigma bond, and now we've generated our new tertiary carbocation. Okay. So the driving force here is to make the most stable carbocation. Okay. And what we'll find out is certain solvents promote this. And so, well, you can have it not shift, you will see the predominant product actually has this shift happen in it. So what happens when you do a methyl group? Well, the same kind of thing here. Okay, so you have a quaternary carbon here, right? You don't have a hydrogen there. We had a tertiary hydrogen up here, carbon up here, and that allowed us to move it there. But what if we had a quaternary carbocation, quaternary carbon next to this secondary carbocation? We're going to do that exact same thing. We're going to move both electrons over one. That p orbital is now going to be above and below this plane. We now have a tertiary carbocation, which is the driving force for this rearrangement. Okay. So questions about this? Okay. As we move forward, you'll see that those different types of reactions we saw at the beginning of the thing, where we have additions across things, displacements across things, eliminations across things, rearrangement, hydrogen shift, protonation, these all are going to be recurring things. These are going to be different steps that happen in all the different mechanisms we'll see throughout our system. One of the harder ones is remembering about this carbocation shift. And the way to think about it is every time you end up with a carbocation, determine whether it's a primary, secondary, or tertiary, and if it's possible to make a tertiary out of a secondary or make a secondary out of a primary. Okay, So then you're always looking for that rearrangement. All right, questions? Okay, so now the last thing I want to talk about is what we call bond dissociation energy. Okay, so in bond dissociation energy, it basically tells you that you get energy by breaking a bond and you store energy by making a bond, right? So the idea here is if you break a bond that had more energy in it than the bond you're forming, you actually are looking at something that is would be exothermic. This is where we can actually start to predict whether a reaction is going to be endothermic or exothermic by looking at that increase or decrease in bond dissociation energy. So it's the general thing is the idea that if a reaction is endothermic, that means that the change in enthalpy is positive, meaning that the more energy is made from breaking the bonds than forming the bonds. So you're not storing as much energy in those newly formed bonds, and therefore you have to absorb energy to the system. Sorry, did I say that backwards? The bonds you're breaking, the bonds broken have more energy than the bonds you've formed, and therefore you have to add energy to the system. The opposite is true. If enthalpy is the exothermic, that means that you have the bonds you've made have less energy than the bonds you've broken, and therefore it gives off heat. Okay, so what we really need to think about here is just look at individual bonds of the one thing that's changing and see whether it's higher or lower energy than the starting material. So what we would do in that case is we just kind of look at some common little changes here. Like for example, if we have just this hydrogen attached to a methyl group right here, it has a bond dissociation of 435 kilojoules per mole. Okay, so that means that if we were to try to pull that off or change that, that's a significant amount of energy required to do so. However, let's look at some other bonds that are maybe easier to break. So let's look at this bond here for like HBr here, okay? So that bond there, that's a bigger, longer bond, and therefore it has a lower energy, of bond dissociation energy, and therefore it's easy to break. Okay. So now let's convert ethylene here, which has a hydrogen bond dissociation of 410, to add the bromine to it instead, and what we'd end up with is the bond. So we're moving from here to here, and that bond dissociation energy is less, right? So what that means is that it's going to actually have a weaker bond, meaning it's storing less energy. So it is going to have a positive impact on the change in enthalpy. Okay? So I just want you to see this is kind of where we can actually predict things that are exothermic or endothermic based on their bond dissociation energies. All right. And that is, I believe, the last slide for this chapter. Yes. Any questions on specifically carbocations and carbocation stabilities? This bond dissociation energy is just kind of wraps up that, that thermodynamics kind of package up in a nice little bow. Okay. All right, I'm going to shift over to the new set of slides that are also on Canvas now. You can have those on Canvas. So now we're going to talk about a specific reaction. Okay, this first section right here was just talking to you about energy diagrams and how to interpret them. The idea that you can have a transition state, that you have that energy required to do it, our activation energy, and the idea that the products and the reactants have different potential energies. Okay. So if you think about it, that those differences in there are the differences in the bonds formed, making from the bond dissociation energy of the reactants versus the products. Okay. So now what we're going to do is we're going to look at a specific type of reaction and use all those different components we found in module 6.1 and are adding those to our new reaction mechanisms. Okay. And so we're going to really look at what we call the SN2 reaction, specifically as it involves alkyl halides. And so it's a great place to start because it lets us use a lot of terminology and get the mechanism down. Okay, so the first thing we want to do is define SN1, or SN2 in this case right here. So the S stands for substitution, okay? So we're basically taking something and displacing something with something else. We're breaking one bond and forming a new one. So that's the substitution reaction, okay? Now we're doing it nucleophilic. That's what the N stands for. So the S stands for substitution, the N stands for nucleophilic. Okay, the 2 is going to stand for bimolecular. Okay, so let's go over and think about this. Okay, many different substitution reactions are known. Anytime you take something that has a neutral molecule and displace it with something else to make a new neutral molecule, that is typically called substitution reaction. Unlike when you have a double bond, you add across it, that's an addition reaction. So you have to actually remove something and add a new bond to get a substitution reaction. Okay, all involve a competition between Lewis bases and Lewis acids, okay? So the idea here is you'll know which way the reaction goes depending on how strong the Lewis acid or Lewis base is on each side of the reaction. Okay, just to remind you, nucleophile is something that likes positive charge. So it's typically something that has a lone pair. It's typically something that might have a charge, a negative charge, and they're always Lewis bases. Okay, so that means the nucleophile, the part coming in with the negative charge or the electrons, is a Lewis base. But not only that, the part that's going to leave is going to become a Lewis base. So if you start with a Lewis base on this axis, you're going to end up with a Lewis base on that side. And you might want to look at it even as the Bronsted-Lowry, it becomes the conjugate Lewis base because it was a neutral molecule at the beginning of the reaction. So all substitution reactions are at equilibrium. Okay. However, in theory, that is true, that all of them can be reversed, but most of the time, because one of the species is stronger than the other, one of the nucleophiles is stronger than the other nucleophile, it'll shift so far to one direction, we won't see the back reaction, okay? So occasionally we won't see the back reaction, but sometimes we do. When the nucleophilic strength or when the base strength of the nucleophile and the leaving group are similar, we will see it not go to completion, and we'll see that equilibrium in our system. Okay, so let's just break down nucleophilic substitution with all its different components. Okay, so the nucleophile is either the thing with a lone pair or a negative charge that is going to come in and displace something on our substrate. Okay, our substrate is our organic molecule that contains some kind of leaving group. In this case, we're talking about alkyl halides, which means we have a straight chain alkane with a halogen on there. So chlorine, iodine, fluorine, bromine, whatever. Okay, so in this particular case, because our nucleophile is the one with the negative charge and the lone pair, the electrophile is the polar bond between the carbon and the halogen. Remember that our carbon is not the same electronegativity as our halogen. I'm going to do fluorine here. And therefore, there is a polar bond, polar electron densities being pulled toward the fluorine. That's making that polar bond, that ability of that fluorine to pull these electrons away from that carbon, the electrophile in this reaction. Okay, so as we go forward in the reaction, as we have that nucleophile come close to the electrophile, we enter what that is the transition state. In that transition state is where we're starting to form the new bond with the nucleophile, and we're starting to break the bond with the halogen that was on your substrate. Okay, so after we go through that, we create our new product, which is our new sigma bond and our new Lewis base. Okay, So we've created our new sigma bond and we've created our new leaving group, or in this case, our new Lewis base. Okay, so that's just the terminology that shows you where everything's going and which electrons are going where. Notice these electrons are the ones that are going to create the new sigma bond. These electrons are going to go away with your leaving group. Okay. So in all these cases, typically you want to have your nucleophile or positive charge loving reagent come in and react. Therefore, and there's typically, it's going to look for something that is either positively charged or a proton, or at least partially positive charged, okay? All nucleophiles tend to be electron rich, i.e. have an anion, like a carbanion, or they must have lone pairs to donate, okay? So you typically have, if you have a charge, like a carbanion or a halide ion, it has that lone pair. Those lone pairs you will see in every single nucleophile, either as a negative charge or as just a lone pair that can come in and react. Okay. So the electrophile tends to be a species that will react with that, but you tend to have a polarized bond. One half of that bond is going to be slightly electron deficient. The other side is going to be willing to accept those electrons. So we're going to see that the electrophile portion of that bond is where the positive side of that bond is, or partially positive. Because as we have that polar bond between the carbon and the halogen here, that means the carbon is the electrophile side of that bond. That means the nucleophile is going to attack the more positive portion of that bond. No matter what that bond is, it's going to attack the more positive side, okay? So in order for that atom to accept those new electrons, it either has to have an empty orbital, like in a carbocation, or it must have something that's going to take those electrons away, a leaving group, okay? So we have two options for us. We can either have an empty orbital / positive charge, or we can have something that will take those electrons away and form a stable ion. All right, so that leaves us to our last thing, and what's our leaving group, okay? So the leaving group is the thing that becomes the new nucleophile, okay? Now, the idea here is you want this nucleophile to be, number one, stable, if at all possible, like a halogen, and you want it to be weakly basic, okay? The reason is that if it's a weak base or a weak nucleophile, it doesn't compete with the original nucleophile to drive the reaction in the opposite direction. So you want your leaving group to be relatively stable and relatively non-nucleophilic. Okay. So let's see. Those are all the terms I think we need to know for our SN2 reactions. Okay. So I said the 2 stands for bimolecular. Okay. In the case of bimolecular, that means that we do not break a bond first and then form a bond. What we're doing here is we actually have to have the nucleophile come in that transition state and start forming the bond while we're breaking the bond with the leaving group. Okay, so if that's a one-step reaction, that means the concentration of both of those molecules is important. Okay, and that's where the 2 comes from. You have to have both materials in the transition state at the exact same time. Okay, so what does this mean? If we look at our rate law, remember our rate law is just some constant that's measured times the concentration of the 2 reagents. Okay, so if our rate law is related to the concentration of the 2 reagents, that means if we double one and keep one the same, the rate's going to double. Okay. If we double both of them, the rate is going to quadruple. Okay. So think about it. Okay. So I have one component, now I have twice as much of these. And so that means there's twice as many of these available to hit that transition state and go to form product. Okay. So it doesn't matter which reactant is doubled, either reactant doubled will double the reaction. But now if you double both of them, now I have twice as many of these and twice as many of these. So 2 times 2 is 4. Okay. So that gives us our rate law is directly proportional to our concentration. So we also have what we call a second order reaction. Now, the reason we say that is that if we looked at the power here, this would be the concentration of this to the first power and the concentration of this to the second power. First power. And if we add those two powers together, that gives us a total exponent here of 2. And we call that a second order reaction. Okay. Because it's dependent upon the concentration of both components, makes it a second order reaction. Okay. So if both molecules are required to make the reaction happen, i.e. an SN2 reaction, and our rate law requires them both to be there at the same time, that means that it is the rate determining step, or the slowest part of the thing, is getting those two reagents in the right position at the right time to start making and breaking bonds at the same time. Okay, questions on that? So substitution, nucleophilic, bimolecular. Okay. All right. So let's look at some just generalized reactions associated with that. Okay. So if all of these involve substitution, okay, so that means we have to have something that we're displacing. Nucleophile, so we have to have something with lone pairs or negative charge. And bimolecular, we have to have the concentration of the two components. Keep in mind when we're doing that. So when we have that, we have the general reaction is an electrophile, which is the thing that's going to be substituted. Our nucleophile, which is the thing that's driving it to do that. Our product, which is our new sigma bond product. And then our leaving group. Okay. Now, the competition between the leaving group and the nucleophile will tell us whether the reaction goes almost to completion or we have some kind of equilibrium. Okay. So a generalized structure here, we typically draw our nucleophile with either at least a lone pair. Sometimes it has a negative charge. And when we draw our electrophile, we show which bond is going to be the one broken during the reaction. And by following these electrons here, we can see those are the new electrons for the sigma bond. And these electrons are the ones that left with the leaving group. Okay, so let's use an actual chemical example. So let's use this one right here, this hydrogen sulfide group here. In this case right here, we have a negatively charged sulfur. We have this polarized bond between carbon and bromine. Notice this partially positive side here. Okay, so that technically that half of the bond is the electrophile, which means the nucleophile is going to have these electrons come in and start to form that new bond. These electrons are going to leave with the bromine, giving us our new product and our leaving group. Okay. So notice where this is coming in. Okay, notice this is coming in from the opposite direction of where the leaving group is leaving. This is very important, okay? If we have this coming in this direction here, okay, then that means that how big these three groups are is going to change our reactivity, okay? In this case here, they're all hydrogens, so they're very small. So they're not going to affect our ability for this group to come in here and make that new sigma bond. Notice the other thing that happened here. If you had your three groups on it in this direction here and you have your nucleophile come in here, what happens to that stereo center? It becomes inverted, like inverting an umbrella in the wind, okay? So because this is coming in here, that big group is going to push all these things flat first, and then they're going to, as soon as the leaving group leaves, they're going to invert in their configuration. Okay. So what does this mean? This means that we have to pay attention to our stereochemistry of our starting material. And when we have an SN2 reaction, we know we're going to get an inversion of that stereo center. But we still have to go back and look at priorities. So, all right. So when a reaction happens all at the same time, when there's only one hump on your reaction diagram, we call this a concerted reaction, meaning bond is being formed while bond is being broken, and never do you have an intermediate. So this is a concerted reaction, okay? So what affects this thing that have it react all at the same time? Well, first thing we have to worry about is the frequency at which the molecules collide with each other, okay? So that's related to concentration, okay? What fraction of the molecules collide with each other with enough energy to overcome that energy barrier? That's activation energy and maybe the heat of solution, how much heat we have in that reaction. And do the molecules collide have sufficient energy and the correct orientation during the collision to cause bond forming and breaking? For example, if you had your substrate with your leaving group on this side, if your nucleophile comes in from this side, that's not going to happen. If you do have it where it's coming in from the backside, but you have three big bulky groups, it's not going to happen. It's going to react very slowly. So the last one is orientation and sterics. So number one is looking at concentration. Number two is looking at activation energy. Number three is looking at sterics and orientation. Okay, so let's look at that in a little more detail. Okay, so when we looked at energy diagrams, we saw that some of them had one hump and some of them had two, okay? In the case of a bimolecular reaction, a concerted reaction, we have one hump because it all happens once and we only have one transition state, okay? So we have to think about that as our starting point. The next thing we have to think about is the outside of every molecule. What's on the outside of every molecule, right? Electrons. So these electrons have to either be polarized to kind of orient themselves in space, or you can think about them as kind of repelling each other a little bit. So if, as I have this species come in toward this species, and all they see, if they're coming in slowly, all they're going to see is that electron-electron repulsion and go and be able to drift apart. However, you have to have enough kinetic energy that as this is coming in, it can push through that electron-electron repulsion until it can start forming that new bond. Okay, so that's where that heat comes in. That heat comes in as giving enough energy for it to push through that electron-electron repulsion to form that transition state. Okay, notice in this transition state here, we don't really have 5 bonds. Oops, we don't have 5 bonds to carbon. And the reason is we have a partial bond on this side and a partial bond on this side. But look what happens to the middle. The carbon in the middle has now looks flat. It looks trigonal planar. It looks like it's trying to be sp2 hybridized, okay? Which means that that p orbital is shifting from that sp3 hybridized orbital is shifting to a p orbital and has a partial bond on either side. And then when this leaves, it now has the sp3 orbital on the opposite side of the molecule, giving us inversion of stereocenter. Okay. So we have to have enough energy to come in and actually break through the electron repulsion to form this transition state. After we form that transition state, it can go backwards. If you don't have enough energy, it can actually cascade back down, giving you starting materials again. So how many molecules in the reaction cascade back to the reactant side? Don't know, but if you give it enough time, it'll all go to product, or most of it. And then when we overcome that barrier, we now have our new starting reaction, okay? Now, if you do not have enough heat or energy or kinetic energy to make that transition state happen, no reaction will occur. Okay, so that brings us back to that temperature argument we talked about. Remember that rule of thumb was that we had to have enough molecules with enough energy to get up that energy barrier to give that, to get to that transition state. And once it got to that transition state, it typically cascaded down to the solution. So in that diagram, we saw that at this lower temperature, let's call this 50 degrees C, right here, the average number of molecules, the average energy of the molecules in there is somewhere about here. Remember, our total energy is related to 50 degrees C, which means all of that energy is distributed over this entire range, but the average is somewhere below the activation energy. Okay, just by heating that reaction up 10 degrees, let's go to 60 degrees here, we've now changed that average temperature to higher. And when we do that, that means we have a greater number of molecules that are above the activation energy here. Okay. So this is where that trying to get just to that transition state, just having enough energy to get into that transition state, and how that temperature affects that system. Okay. So then the next thing we have to talk about is the fraction of collisions that produce product. Okay. Now, so we have collisions happening in space, and they're all coming in random directions with different amounts of energy, right? So if you come at the wrong orientation, such that the two, the leading group and the nucleophile are coming at the same direction, that's a non-productive collision. It's not in a position to actually make a reaction. Okay. So let's think about that. If we only had 7 collisions per 100 trillion, having the significant energy to convert to products, what does this mean? Okay. Well, that means that if we increased the temperature, that would significantly increase the number of collisions available to us. Okay. Which means that just by raising the temperature, in this case, we're raising it 10 degrees. We're going from 298 Kelvin to 308 Kelvin. We actually increase the number of collisions by 3 times 3, okay? Which means that 10% that increases the number of possible collisions 3 times. And in general, that doubles the number of productive collisions we have. Okay, so this collision theory explains why the reaction rates are actually lower than collision rates, because not every collision is in the correct order, and not every collision has enough energy. Okay, so the collision rates increase with the increasing temperature, but only by a small amount. Okay, so it was 2%. Even if the molecules collide with enough kinetic energy, all the reactions that occurred in the molecule, because they're not aligned correctly, they're like hitting where the leading group is, and that's a non-productive one. Even though it's 3 times the collisions, it's just doubling the number of actual productive reactions. So, all right. So the next thing that we have to worry about, because when we're coming in there, we have to come at the back side of that polarized bond where that electrophile is. So that means that the groups that are interfering with this coming in and aligning itself to give us that thing is now a factor. We call this the steric factor. So the first thing we had was kinetic energy, allowing us to get to that transition state. Now this is the steric factor to get to that collision state. Okay, so as the size of these 3 groups that are on that backside of this this polarized bond get bigger, that means very few molecules are going to be perfectly aligned to come in and get into that space. Okay, so I'm not going to go through the equation, but the idea here is that as the air, let's say you had 3 small hydrogens right here, and so that when you had a large group coming in here to do the substitution reactions, there's very little electron density repelling them, and they can come in here and form that collision that makes the productive system. Now let's change those 3 little hydrogens into 3 little methyl groups now. So now you have 3 methyl groups here, and now it has to overcome the sterics, the electronics of all of those hydrogens around here. It has to be able to get just in like the right little spot, little cone of attack where it can do this, okay? And so that can actually be explained using the Arrhenius equation here. I'm not going to go through that because we're not going to do any of these calculations, but I want you to know that the the steric factor is going to be a big factor when we look at reaction rates. Doesn't mean it's not going to happen. It just means it's going to slow it down because the number of collisions goes down as you make these groups larger and larger. The number of times that a molecule can come in that exact right angle goes down. Okay, so let's look at that a little more visually, you know, without looking at my hands here. And in this case here, let's have an example of this nucleophile number 1 coming in and attacking here. So in this first case here, it's coming from the wrong side. It's not coming toward the backside of that polarized bond. It's actually coming toward, oh, we've gone over time. I'm sorry. All right, we'll pick up here tomorrow. Wow, that went fast. Okay, so we'll pick up where potential energy coordinates start here and next time. So I'm sorry, thank you for reminding me. All right, I'm gonna go ahead and stop recording.